Welcome back. If you just look around you, pretty much everything, standing buildings, bridges, you name it, it's all down to structural engineering. It feels ancient, right? Built on solid physics.
Absolutely. Hard rules, material science, things we've understood for centuries in some ways.
But today, we're doing a deep dive into something really shaking those foundations. We're unpacking how advanced AI, specifically deep learning, it's colliding with this old school industry.
And changing it fundamentally.
Yeah, completely redefining how we think about building sustainably. Our mission here is really to give you the shortcut, the core understanding of this shift. How deep learning is already, and that's the key part, already delivering designs that are greener, safer, and often cheaper.
And sometimes looking completely alien, honestly. Shapes humans maybe wouldn't even sketch.
Exactly.
Yeah.
Which brings us to that central finding from the sources we looked at.
Right, this isn't just lab research anymore. Deep learning technologies are genuinely making big strides. They're generating innovative, sustainable designs now.
Using techniques like generative design you mentioned. Solving problems in totally new ways.
Precisely. It's moving past the standard rectangular way of thinking, finding efficiencies in materials we just didn't see before.
Okay, let's ground this a bit. Deep learning. We know it's AI, handles huge data sets. But for our listeners who are pretty tuned into this stuff, let's skip the 101.
Good idea.
For structural systems, where everything's connected, beams, frames, slabs, what specific kind of deep learning are we actually talking about here? It can't just be a standard neural network, can it?
No, exactly. You can't just feed it costs on a spreadsheet. The real challenge, the complexity, is that interconnectedness. You push here, something moves way over there.
Right.
So what the industry is leaning on heavily now are things like graph neural networks, GNNs.
GNNs, okay.
Yeah, think of a complex structure, like a bridge truss. It's nodes and connections, right? A graph.
Makes sense.
GNNs are built for that. They understand relationships between data points, not just the points themselves. They process the structure as a graph, which means they can assess how, say, stress or vibration moves across every single connection almost instantly.
That clicks.
Yeah.
It's modeling the system like it actually behaves, not just approximating sections.
Exactly.
So if GNNs are handling the complexity, how does that translate into better designs? Because traditionally, engineers face that constant trade-off, right? Strength costs more, complexity takes ages to calculate.
Right. And that initial calculation bottleneck is where AI just shines immediately. We hear viability assessment, but what the sources really describe is a very sophisticated optimization.
Okay.
The algorithm's job is basically finding the absolute minimum material needed to hit all the safety targets.
Minimum material. Does that mean these structures look weird?
Yeah.
Because our intuition usually goes for thick, symmetrical, safe-looking designs.
Oh, absolutely. Often wildly different. This is where generative design really comes into its own. The AI runs maybe millions of iterations. Yeah. And it often settles on these non-linear, organic-looking, almost fractal shapes. It's purely driven by where the load goes, where the stress is.
Like nature does it. Own structure, tree branches.
Exactly like that. Material only where it's needed. And the sources show these algorithms are creating designs for, say, specific beams or foundation parts that use maybe 20, even up to 40% less material than the standard human-designed equivalent.
40%. That's huge. But hang on, I need to push back a bit here. An engineer sees a design that looks like, I don't know, an alien rib cage.
Yeah.
You might be a bit skeptical, right? And what about the cost? Training these models, getting the data, integrating it, the sources must touch on that.
Oh, definitely. That's a very real hurdle. Integration is complex. The upfront investment is significant. Software, training people, and crucially, getting the right data. You need loads of high-quality performance data from existing structures.
Right, the input matters.
Hugely. But the argument in the sources is, once these models are trained, the speed you can iterate at. The ROI just blows traditional methods out of the water.
Okay.
And it's not just strength and cost anymore. AI easily pulls in that third critical factor, environmental impact.
The triple bottom line idea. So what does that environmental piece actually mean when the AI is calculating? How does it calculate green?
It boils down to integrating embodied carbon modeling right into the design loop.
Embodied carbon, okay.
Yeah. Every material choice, steel, concrete, timber, has a carbon cost attached. mining it, making it, shipping it, installing it.
Right, the whole life cycle up to that point.
Exactly. So a traditional approach might say steel is cheaper here and strong enough, done.
Mm-hmm.
The AI might explore, okay, what if we replace part of that steel with this new locally sourced lower carbon concrete? Or what if we change the shape entirely to use less steel overall, even if the shape is really complex?
So it's weighing the environmental cost alongside the dollar cost and the performance.
Precisely. Right from the very first digital sketch. It connects performance needs with sustainability goals early on.
That really changes the game, designing not just structures but optimal material flows guided by carbon budgets, which I guess makes the old way look incredibly slow.
It really does. The traditional method is, well, it's linear, it's resource heavy. An engineer sketches maybe 3-4 options, runs complex simulations, FEA, finite element analysis on each one. That takes time.
Hours, days sometimes.
Easily. Then they pick one. If that fails, a cost review, or maybe a late-stage environmental check. Back to square one.
And historically, hitting safety standards often meant just adding more material, right? Over-engineering was rewarded in a way.
It often was. Brute force safety, which means excess material, means higher embodied carbon. It was almost baked into the process.
And don't forget physical prototypes.
Oh, absolutely. For anything really novel or complex, you often needed scaled models. Physical testing. That's time, money, and a lot of wasted material just in the design phase.
Okay, so traditional is trial and error, slow calculations, physical stuff. How does deep learning change the efficiency game through simulation? What's getting faster?
It's the acceleration of those sophisticated analyses, like FEA, what
Yeah.
used to take hours or days on a powerful computer.
Yeah.
The DL models, having learned the underlying physics and material behaviors from all that data, they can essentially run these incredibly complex stress, strain, and failure analyses as part of the design generation.
Integrated directly.
Yes, often cutting simulation time down to minutes. So it's not simulating one design slowly. It's generating, analyzing, and optimizing thousands of valid designs in the time it took a team to fully analyze just one before.
That's pattern recognition applied to physics, essentially.
You could say that, yeah.
And for you, the listener, the relevance here is pretty stark. If design teams can rapidly find ways to meet safety rules using less high-impact stuff like cement or new steel, they're actively cutting material waste and the energy used in construction. Big time.
And it goes beyond just day one. The process lets engineers simulate the whole life of the structure much more easily.
How so?
They can assess how things perform not just under maximum load, but how they might degrade over 50, 100 years given local environmental conditions.
Okay, this feels like it's leading us into the future toolkit idea. If these models keep getting better, we're not just optimizing the initial build.
Yeah.
What's the scope for looking at that long-term environmental footprint?
It gets much broader. Think predictive maintenance, operational efficiency. An AI-designed smart structure could come with its own optimized maintenance plan.
Really? How?
The AI can predict, based on known material decay rates, climate data, usage patterns maybe, when specific parts might need checking or replacing. We move from fixing things after they break,
Which is expensive and disruptive.
right, to proactive, data-informed care of our infrastructure.
So we could end up with buildings that are just inherently more efficient to run heat. Cool, because their very structure and materials were optimized from the start. And cheaper, greener to maintain over decades, because the AI basically wrote the service schedule.
That's exactly the path we're on. The structures themselves become sort of living data systems. The sources strongly suggest that within, say, the next 10 years, these AI design tools, they won't be niche.
They'll be standard.
Standard kit, an essential part of the engineering toolkit. Competence will mean being able to guide and refine these AI models, not just crunching numbers manually.
That's a huge shift in what it means to be an engineer. From
Yeah.
calculator to maybe conductor of the AI orchestra.
That's a good way to put it, yeah. The big takeaway seems to be that deep learning is forcing the industry to finally merge performance, safety, and sustainability into one unified process.
Right.
It ensures that what we build next isn't just strong and safe, that's the baseline, but provably greener and more efficient. It's redesigning how we build against gravity, but at computation speed.
Synthesizing goals that used to conflict.
Exactly. One optimized solution.
So, summarizing this deep dive, we're seeing structural engineering move from slow, often overbuilt, prototype-heavy design to rapid simulated optimization, guided by complex data on stress, cost, and that crucial embodied carbon figure.
Yeah. And the knowledge for you listening is that the physical world around us, how we build everything from apartment blocks to train lines, is undergoing a fundamental redesign. This shift means the infrastructure supporting us all can become greener almost by default.
Okay, so here's a final thought to leave you with. If AI can optimize building design so rapidly, exploring thousands of options, slashing material use, producing these sometimes bizarre but super efficient shapes, what other big physical industries are next? Think about sectors still relying heavily on those traditional linear calculations and multiple physical prototypes, maybe aerospace parts or complex manufacturing tools. Where else will AI force a complete rethink of how things get designed? Something to chew on. Thanks for diving deep with us today on how AI is reshaping structural engineering.